however it comes out, there's something weird going on in quantum mechanics. We know that because of the violations of Bell's inequality, right? The quantum mechanical world, the world we live in, has some very counterintuitive or unusual or unexpected features, much more than you ever got out of Newton or out of, Maxwell or out of Einstein. What I would say to Einstein, I think I wouldn't even have to say it. I like to think if Einstein had lived a few more years and seen Bell's result, and then seen the outcomes of the experiments, he would have been convinced. What he didn't like from the beginning about quantum mechanics was the non-locality. It's very clear. It wasn't the indeterminism, it was the non-locality.
Tim Maudlin is a professor of philosophy at New York University, and he's the author of several books, including Quantum Non-Locality and Relativity, Truth and Paradox, Solving the Riddles, The Metaphysics Within Physics, and Philosophy of Physics, Space and Time. He's also been very interested primarily in foundational questions, particularly foundational questions in science, and more especially foundational questions in physics. So, Tim, thank you very much for joining me today.
Thanks for having me.
Can I start by asking you how you became interested in foundational questions? Because most of the scientists that I speak to tend to be more interested in whether this piece of equipment works or whether I can get a better result from that particular by tuning these characteristics. It's rare to find someone interested in foundational questions. How did you come to that as your main interest?
Well, I think that's just a matter of personality. I have kind of all kinds of interests, but when I was an undergraduate, I did a joint degree in physics and philosophy. And then my PhD is in history and philosophy of science. And from a certain perspective, physics and philosophy, at least physics as I am interested in it, go together perfectly well, because in both cases, in a certain sense of the bottom, you're trying to get to the bottom of things, right? So there's a state of mind, and it's a particular state of mind that says, well, really biology is just fancy chemistry, and chemistry is really just somehow fancy physics. And that's not really right in lots of ways, but there is a sense in which it's right. And so if you're pursuing this, what lies beneath that, or what lies at the bottom, in the sciences, there's a way of doing that where you end up in physics. And then as a general approach to all of life, you end up in philosophy, right? What's at the bottom of all this? What are the fundamental presuppositions here? How could they possibly go wrong, and things like that. So yeah, I think that's a very natural instinct that many students of physics have, and they often have it beaten out of them or abandon the field because their physics professors are not interested in these questions, which are the questions that originally motivated them, right, to be interested in physics. So,
and then they get led down the path of more practical applications of things
practical,
like
you can go practical, or you can go shut up and calculate, right? Learn to solve the math and don't ask yourself what it means.
But the difficulty though that many scientists have, I suppose, is that a lot of stuff is driven by bidding for money and for grants and different things, and most of those are tied to practical outcomes. They're not that interested, are they, in foundational questions?
Yeah, there's the part of it that connects up to industry and people making money and making faster computer chips. But even on the purely theoretical side, you think of the Large Hadron Collider. Nobody built that because of thinking there was going to be a big practical payoff. Even there, in kind of what you think of as more pure physics, the interest in really the kind of foundational questions I'm interested in isn't very manifest.
Tell me, moving into philosophy, do you find there's any antagonism from, let's say, the pure physicists to the philosopher? Do they look down on philosophy?
It certainly used to be the case in a very extreme way. that, I mean, Feynman famously mocked philosophers and insulted them and so on. Although, to be fair, I think some of the philosophers he was dealing with probably deserved it. I don't, there's been progress on the side of philosophy too, of philosophers understanding if they wanted to think about the physical world, they better learn some physics and not just do it from some a priori, navel gazing attitude. But I think a lot of it was just this weird historical remnant of quantum theory and a lot of damage Bohr did with his sort of pseudo philosophy, which discouraged physicists from straightforwardly addressing certain questions that many people are interested in. And then when you can't answer the questions, you often react by mocking the questions themselves, right? Because it's a little embarrassing not to be able to have straightforward answers to them.
Have you, in your studies of both philosophy and physics, have you been able to find a strict criterion of demarcation between the two? Popper spoke of a criterion of demarcation to distinguish science from non-science. Is there such a criterion of demarcation between physics and philosophy? Is there a sharp dividing line, or is it just fuzzy?
Not only did I not find one, I'm constantly arguing that there isn't one, and you should stop looking for it. There's a branch of philosophy that goes by the name metaphysics, but if you look at what Aristotle was doing in the manuscript that comes down to us under that name, he never used that term. His interest was in just what exists, in, as he says, being qua being, or being in as such. That is, at the highest levels of generality, what sorts of things exist. And obviously the physical world exists. And so an attempt to really understand what it is fundamentally is doing metaphysics, is doing a topic that's central to philosophy. And to do that well, you have to consider the results of physics. And so I often say my field is foundations of physics. That doesn't have the word philosophy in it, but it fits as well in a philosophy department as in a physics department. Well, better in a philosophy department because physics departments won't employ people doing that, and philosophy departments will.
Yeah, I thought that you might suggest that there was a sharp distinction between physics and philosophy on the lines of empiricism. Something which can be measured and checked might fall into the physics category, and something which can't be measured and checked would fall into the philosophy side. What would you say to that criterion?
Well, there was a long period when the logical positivists, the Vienna Circle, and in a way Popper in a slightly different way, were trying to run that line, and it failed. It just, you can't work it out in a coherent way because claims from physics can't really be checked without all sorts of presuppositions, which themselves are going unchecked. It just makes it too simplistic to think that empirical data will settle this set of questions and can't touch that set of questions. Really, what happens is usually empirical data has more immediate, obvious, direct bearing on making certain claims plausible and implausible, and less direct bearing on other claims. But again, that's just a continuum. And in the philosophy of science, I mean, in philosophy itself, Quine was arguing against the analytic synthetic distinction, arguing against this bifurcation, which is taken for granted by some older philosophers. And so the philosophy I grew up with, that bifurcation just wasn't even defended.
Fair enough. But aren't there some questions which, in principle, cannot be provided with a measurable answer, and some questions in principle which can? I mean, take a trivial example. I've got a fridge over here, and the fridge, every time I open the door, there's nothing in it. But when I close the door, there's a pink elephant in there. But every time you open the door and try to observe it, you can't see it because it disappears. I mean, in principle, you can't answer that or test that question. It becomes untestable as such. And you might put that into the realm of metaphysics and philosophy, possibly. Whereas other things are intrinsically testable, like what's the gravitational pull on the moon, for example. Those kind of things can be measured.
Well, let's just take the narrow question of measurement. At base, I would claim physics operates under the assumption there is a universal physical state of the entire universe. In fact, often that's what you need to plug in to the fundamental equations, and not something limited. Is it even theoretically possible to measure the precise physical state of the entire universe? The answer is no, because there's no place you can stand to do it, right? You'd have to stand outside the universe to do it. Okay, so that's a fundamental positive physics that can't be measured. Now, you can get at it to some degree. The reason not to think there are pink elephants in my refrigerator when the door is closed are certainly, among them are lots of empirical observations, namely things don't just come and go and so on. And then if someone says, well, what if they only come and go when we look at them? And then you say, but our looking is just another physical interaction. Why would the world suddenly change the way it behaves? Oddly enough, it's quantum physicists who sometimes say that, right? That the world behaves entirely differently when people are looking at it. I think that's silly, right? David Merman once said, we've now proven the moon doesn't exist when we don't look at it, but that's just silly, right? We all know the moon is there when nobody's looking at it. But he was a physicist, right? Not a philosopher. Yeah. So I think, the general reasons for thinking your pink elephant theory are not worthy of any credence. Are they empirical? Well, to a large extent, there's a lot of empirical information we have about elephants and what they do and things popping in and out of existence that make that an entirely incredible hypothesis.
That of course implies those kind of causality and chains and things which David Hume spoke about and said that, well, they can't really you can't really demonstrate causality as such, doesn't he? You have to assume it well,
sure, but Hume also said you can't demonstrate there's an external world at all, right? A physical world. So he would say physics rests on an equally unprovable assumption, if you want to put it that way. So trying to demarcate philosophy from physics in that way, again, you're not going to get a sharp line.
Okay. Now, let me ask you this question instead. Let's move on slightly to in the fundamental questions area. What is fundamental, or what is foundational in Tim Maudlin's universe? I mean, in other words, what exists at the lowest irreducible level? Does space exist? Does time exist? Or are these things derivable from other things? What is the lowest beable, to quote Bell?
Yeah, I mean, I think that's a wonderful question. Of course, whatever it is in my universe, it's the same in your universe, because we live in the same universe.
But please say you say that.
The question is, what are plausible hypotheses about these things? Where is and you immediately see any physical analysis or any analysis has to stop somewhere, right? Yeah. It has to stop at some level, which is the unexplained explainer, in terms of which you then account for everything else. And that always raises the question, well, where do I stop? I mean, maybe there's something deeper than what I've thought of so far. And it's always a judgment call, right? I mean, this is not the kind of thing that's subject to proof. What I would say is that the physics, the way we understand the physical world right now, and I don't see prospects of anything terribly different, have a space-time structure, which is, at least at large scales, four-dimensional and has a temporal aspect and a spatial aspect. Those might be mixed together in the way that relativity has taught us to think about, but a space-time structure.
But you wouldn't. What would you make of those physicists who are seeking to derive space-time structure from something else? I mean, Penrose tried twistors. Other people have tried different approaches to construct space. And Bohm, I think, was also one of those people who tried to create more primitive geometries, or something from which geometry itself would be created from.
Right, and this is the kind of thing, if you describe it at that generic level, I can't say I know it's not possible. If you have a proposal, I'll sit and listen to it.
Okay.
Look, Penrose found twistors mathematically, and he's been looking for some physical job for them for about half a century, and he's still looking. He just gave a talk last week in Rutgers saying, oh, here's maybe something you can use twistors for. Maybe there's something, but, and I'll listen, right? So I don't have a proof. That's what I was saying. I don't have a proof there might be something from which these things I'm taking as fundamental emerge.
But you're
I
not looking for
personally
anything.
don't see any very good prospects for that, and I'd rather take them as fundamental and try and map out what their fundamental structure is than try and think maybe there's something even beneath that.
Okay,
Right?
so you take space and time as given fundamental structures. What else
Yes.
would you add
So-
into that mix? Things like charge and
So what we need on top of that, just to have a possibly adequate theory, are what John Bell called local beables. That is, some kind of physical things that can be located in small regions of space-time, right? Because it's in terms of the arrangements of those that we can say, oh, that's a table, that's a chair, that's a piano, right? That's a pointer that went this way rather than that way. So we need those two things. And then we need whatever else we need to give a good dynamics for those things, right? To account for the motions. If you think physics is the theory of matter in motion, which is a definition that was long given, you'd say, well, then I need an account of what matter is. That's the local beables. And we need an account of motion. What do I need for that? That depends on how it goes. Quantum theory certainly suggests I need something very different, right? Something Aristotle never thought of, something Plato never thought of. That's represented by the wave function, by this mathematical thing called the wave function. That doesn't seem to be a local thing. I'm perfectly happy to take that as a new primitive kind of thing, that it doesn't get analyzed in terms of anything else. But if you give me a space-time structure and some local beables and a wave function, I can write down dynamics in terms of that. I need the space-time to write down the dynamical equations. I need the local beables to give me empirical content. I need something like a wave function to give me the dynamics of the local beables. Right
Okay.
now, it looks to me that might be enough.
So what you've got then in the universe is a set of entities, whatever they may be, space and time, beables, and those entities are then related by some kind of functional equation, Schrodinger's equation or something of that nature that you've mentioned, the wave equation. Does the relationship itself, do the equations which relate these beables, are they irreducible? Are they accidental? Are they telling us something about the universe itself, or are they telling us something about a random world? For example, let me give you an example. Supposing the universe is no more than a flat plane with random dots on it. That's all it is. Mm-hmm. You might well find that you can see a law in that randomness by saying that, well, any two dots can be connected by a straight line. Mm-hmm. And suddenly you've got a law which connects those things together. But the law itself is no more than a property of, I suppose, the space, not something which really connects the dots together.
Right. Yeah, so I have very definite views about this. And
tell me, I'm interested.
I didn't mention. Yes, I think, and you'll get a lot of pushback from philosophers, maybe more than from physicists. I think that part of what exists are fundamental physical laws, and they don't have the status that you just suggested of being emergent or merely descriptive. Okay, so Schrodinger's equation, the mathematical equation, I take to be an attempt to express a physical law of how, say, a quantum state evolves in time. And that its status as a physical law is, again, a fundamental thing. So there are lots of philosophers, starting with Hume, who wanted to reduce lawhood to something else, right? Yeah. To say, well, lawhood is nothing but just being a pattern. But I think of it the other way around. I think there's so much patternedness in the world because it was generated in a gnomic way, right? It was generated by a law like Schrodinger's equation, or like the guidance equation, or like, F equals ma. There's sorts of things in a physics class. Again, the physics professor would just say, well, here's the law, right? F equals ma. I don't have a further story about what makes it a law, but let's at least just take for granted right now that it is a law.
But
And therefore we can say what would happen under various non-actual circumstances, right? How do I know if I had let go of the bottle, it would have fallen? Well, because it's a law that F equals ma. And if you let go of it, then the total force would be the gravitational force, and then it would accelerate downward or something like that.
But here's a point, though. I mean, take Newton's simple gravitational inverse square law.
Mm-hmm.
The inverse square law itself is really probably got nothing to do with gravity as such. It's more to do with, surely, it's an aspect of three-dimensional space. It's the fact that as you move out from space, things drop off as an inverse square because of the nature of three dimensions itself. It's a three-dimensional effect. And if that's the case with an inverse square law, why might it not be the case with a wave equation, for example? It's just a property of some space or the universe that we're living in, rather than something fundamental relating things together.
So let me take the Newtonian example. Of course, we know Newton was wrong, and we're doing kind of fantasy physics here, but let me stick with that because it's easy. When you say, well, isn't it just a property of the geometry that things fall off as r squared? But what things, right? You mentioned things. Now, what is creating this force? Now, Newton himself actually believed it had to be some kind of particles. I mean, he rejected action at a distance. And it may be if you have some particles that are, as it were, transferring the gravitational force, and you then have the laws of how those particles move, you might be able to show geometrically that the amount of force is going to drop off as r squared. I think Newton probably thought that's correct. Of course, in Principia, he says, I'm only going to prove what I'm only going to mention what I can prove from the phenomena. And that's where he says hypothesis non fingo, right? I can't prove what the cause of gravitational force is. I just can prove it's there. So sure, geometry could come into it, but it can't be a purely geometrical explanation because there has to be something, the thing that's dropping off, right? That you're applying the geometry to, and that's going to be a piece of physics.
Right. Okay. And of course, that's been replaced by things like fields now. And
and gravity has really been replaced by curvature of space-time in the general theory of relativity. I mean, there, lots of different ways you can go.
And do fields in Tim Maudlin's universe really exist as real physical things, or are they merely mathematical conveniences?
Well, I would say somehow my view is our best guess now is that quantum theory is the nearest thing we have to an adequate account of physics. And as I said, it needs this funny thing called a quantum state, and it needs it whether you're doing quantum field theory or quantum mechanics or whatever kind of quantum X you're doing. You need a thing described by a wave function. So that's physically real. And then you need something, these local beables, as Bell would say. What are they? Well, they could be particles, which is what you do in the Bohmian mechanics or pilot wave theory. They could be more field-like. Then you have a kind of pilot wave field theory. Then there would be a local fact in every little region of space-time. What's the field here? What's the field there? The way you think of an electric and magnetic field in Maxwell's picture. So both of those are possible. I don't know which way it goes. I think there has to be something local, and I'm perfectly willing, again, to listen to somebody who tells me it's a particle, somebody who tells me it's a field, somebody who tells me it's a string, somebody who tells me it's a point-like thing, which we call flashes, the flash ontology. Lots of possibilities, and I'm open to all of them.
In being open to all of them, though, you nevertheless, if I've understood you right, you come down on the idea that quantum mechanics is describing something real at bottom, that it's an ontological theory rather than an epistemological theory. It's something which tells you about what is, and not merely about what we can know.
Right. Yes, it is not a piece of epistemology.
It's not, because the Copenhagen interpretation may well be considered in that kind of way, whereas Bohmian mechanics is often thought of as the ontological interpretation.
Right. But the epistemological one runs into just empirical problems, and people have pointed this out forever. So you use a wave, just for the regular two-slit interference, you use a wave function, right? We all agree how to calculate it. We propagate it through the two slits, and it's spread out. Now, some people say, well, maybe the spread outness is just a reflection of us not knowing where the particle is, right? But then you say, but then how do you get these interference effects? You know, because your ignorance went through both slits? That doesn't make any sense at all. Something physical had to interact with both slits, right?
Yeah.
And there's even this, theorem by the PBR theorem by Pusey, Barrett, and Rudolph, which more or less rules out, I would say, these epistemological or accounts of the wave function. Basically say they're just incompatible with plain predictions of quantum theory, in much the way that Bell's theorem rules out local theories. They're just incompatible with the plain predictions of the theory. So I think the problem was Bohr and a lot of those people were sort of double thinking. Sometimes they would treat the wave function as physically, not just physically real, but the bottom of everything and complete. I mean, this is what Einstein was complaining about. They treat it as a complete physical description. And then sometimes it's kind of quasi-epistemological, but then it wouldn't be a complete physical description, because to say that it's epistemological is to say it's just about how much I know, not about how much there is. If that was really their view, then they should have said to Einstein, of course it's incomplete. Maybe we don't think we can ever know anymore, but there is more. But they didn't say that. They rather insisted, no, it's complete. There can't be any deeper description.
Because there was no more to know.
Exactly.
Yeah. And it's like an impenetrable fog around everything, I suppose. But in that sense, then, I mean, quantum mechanics is quite an unusual theory insofar as it does have many different interpretations. I mean, Einstein's general relativity doesn't have many different interpretations, but quantum mechanics, people look at it in terms of a Copenhagen interpretation, or they look at it from a Bohmian point of view. They might even look at it from an Everett Wheeler many worlds theory. Or there's a relational idea, which Ravelli is now championing. Do you have a view on why there are so many different views of quantum mechanics, and why it isn't as simple and straightforward as relativity might be?
Right, and I think, I mean, the first thing is I've been fighting, I'll never win. I don't like this language of interpretations of quantum theory, because when you say that, it suggests, okay, we have a theory and we're just missing this other thing, whatever it is, an interpretation, which sort of sounds philosophical. I don't think we have a theory. I think what a physical theory is, what Bell would call professionally acceptable, precise physical theory is, should tell you, according to that theory, exactly what actually exists and how it behaves. What we have is a predictive formalism that everybody uses, and that involves a wave function and Schrodinger's equation, at least most of the time, but maybe not some of the time if there are collapses, and everybody sort of knows how to use that formalism to make predictions. But that's not a physical theory. A physical theory would be telling me what there is in the world that behaves that way and exactly how it behaves. And so what we really have are just different theories that all give almost either exactly or almost exactly the same predictions. And then there's a fight over which of these theories is more likely to be closer to the truth. And this, again, this is all physics, but you can't just go into a lab in an easy way and decide. There's some cases in collapse theories where they make slightly different predictions. And you can go into a lab, and they're doing that in Gran Sasso. I mean, there are certain experiments that are putting pressure on the collapse theories from a completely empirical point of view. In other cases, it's not clear. Any experiments will tell you this is right and this is wrong, right? You could have two different theories that make the same predictions. Why are there so many? Well, I think because it's the quantum, however it comes out, there's something weird going on in quantum mechanics. We know that because of the violations of Bell's inequality, right? The quantum mechanical world, the world we live in, has some very counterintuitive or unusual or unexpected features, much more than you ever got out of Newton or out of, Maxwell or out of Einstein. I mean, really, general relativity is a kind of classical theory in spirit. And I think there's so much debate because people have a hard time trying to come to terms with what it is exactly they want to give up or what they're willing to accept as the fundamental weirdness of quantum theory.
Yeah. I have to say, I like the idea that you just presented, that it's not one theory with many interpretations, but it's many different theories. But
Yeah.
what would you say to the argument then that if you've got two separate theories, which produce exactly the same answer, there's nothing to distinguish between them.
Mm-hmm.
I'm thinking, for example, of Schrodinger's equation predicting the results of quantum mechanics, and Bohmian mechanics, which is no more than merely a separation of the Schrodinger equation into its real and imaginary parts. So it's purely a mathematical device to separate it out into two equations. It must therefore give exactly the same results because it's essentially just a real and imaginary part. And yet you've got two different theories doing exactly the same job. How can you have an idea of reality then expressed by two different theories which are indistinguishable in terms of their results?
Okay, so there are two parts to that question. Let me take what I think is the more important one first.
Okay.
I don't think of the relationship between standard quantum mechanics and pilot wave theory the way you just expressed it. Why is that? Well, of course, in both cases, they're non-collapse theories. You have a wave function. It always evolves by this linear equation. They agree on that. In the standard case, if you say, yeah, but how do I even get predictions out of this thing? The normal answer is, well, when you do a measurement, then you have some Hermitian operator, and there's a gadget for extracting probabilistic predictions using this Hermitian operator, blah, blah, blah. In the pilot wave case, you say, well, look, according to this theory, the world is made of these particles. They're moving around in a certain way. Try and analyze how they should move around in this particular experimental setting, right, to get your predictions. How do these differ? Well, and this is something that's very active right now, take the idea of an arrival time, right, or a time of flight. I release a particle, there's a flash on the screen, or there's a distribution of flashes. And normally we'd say, well, why did those flashes occur? Why did they occur in this pattern? In the case of Bohmian mechanics, where you actually have a real physical particle that goes from here to there, you can ask questions like, well, according to the theory, how long should it take? You can do calculations. In standard quantum mechanics, there is no particle. There's nothing that arrives, right? And there's no time operator. There's no Hermitian operator you can use. There's no agreement even in the literature about how to do calculations. There are different proposals that tend to agree in far field scattering, but disagree in near field scattering. It's a complete mess. So the relation between those two theories is not as transparent as you're making out that, gee, they're really, making the same predictions. I would say in that case, they're like clean Bohmian predictions, and the standard theory doesn't really even know how to begin to make predictions. The other thing to say is sometimes you can say I have two theories or two postulates that are clearly can't be distinguished empirically, but are not at all equally plausible. So this is a very fanciful notion. Here's a hypothesis. The entire universe just began 30 seconds ago. And it began in the state it was 30 seconds ago, but we never had the beginning of this conversation, right? We were not talking to each other. Of course, something that purports to be a recording of it will show up on your hard drive because it was there at the beginning, right? Now, it's clear, you might say that's a fanciful thing. Okay, but it obviously disagrees with the theory that we have been talking for half an hour. And obviously no experiment will be able to refute it because I've set it up to be kind of empirically unrefutable.
Yeah, I mean,
But the right thing to say is it's a lunatic theory. Why would I believe that, right? It's clearly much more rational to believe that the universe has been around. We've been talking for a while, and the recording really is a recording of something that happened. So,
the difficulty you have, though, is you say it's a lunatic theory, but what actually makes it a lunatic theory? What is the evidence for that? Why isn't it just good?
In that case, I would have to postulate, first of all, that the universe came into existence in a very, very, very special state with all kinds of very precise correlations between things which have no explanation, right? Because the initial state of the universe, its structure can't be explained by how it evolved, because by postulate, it's the initial state. It didn't evolve from anything, right? So usually what we do in science is we postulate things, new things, to explain correlations that are there, but we don't seem to have an explanation for. There's all kinds of explanatory projects that are central to science, explaining the structure of the world. And often we postulate neutrinos. Why? Because we could see them? No, we couldn't see them. But if we didn't have them, for example, in that case, you get violations of conservation of energy, you get violations of conservation momentum. So you say, gosh, it seems much more plausible that there's a little tiny neutral particle we're not seeing. And then when you're clever enough and you can build detectors, eventually you find it. But the original plausibility of that theory was not empirical, right? It was just, with them, I can have a much more satisfactory explanatory physics than without them.
Yeah, okay. I take your point on that. Come back, though, with me to the different quantum mechanical theories that we're talking about here. Does Tim Maudlin lean towards one of them as more correct or more accurate than another?
Yes. And I mean, you can break these down. I mean, I did this in a paper a long time ago and say, essentially, you have to ask the question, you're going to have something like a quantum state. I mean, the wave function plays too central a role in making all these predictions to just...
By a quantum state, you mean something which has the property of superposition?
Yes, a physical thing that's described by the usual wave function we use in the formalism, and that does superpose under linear evolution in the normal way, right? It's governed by a wave equation. It will superpose in the normal way. Now you can ask some just yes/no questions. First question, does it ever collapse or does it not collapse, right? Is it always a linear evolution, like Schrodinger evolution, or does it sometimes do something different? I think I can see both possibilities. Penrose certainly had a collapse idea, wanted a collapse idea associated with gravity.
Yeah.
Girardi, Rumini, and Weber have a spontaneous collapse theory. There were these weird consciousness collapse theories. Yeah. I just don't think collapse is very plausible to me. It doesn't smell right, right? I'd much rather have a clean, universal, linear evolution of that.
In which case you're moving towards many worlds?
Well, then the second question is there anything more than is described by the quantum state? The many worlds people say no, and that's how they end up with many worlds. They don't have collapses, and then they get these many worlds. The pilot wave theory says, yes, there is something else. Particles or fields or whatever, these local beables, they don't split, they don't multiply. They give you one world, but the things behave quantum mechanically. And to me, that all just seems much more plausible. So I would go that direction, a kind of pilot wave, under the pilot wave umbrella. Now, there are lots of details that you can go different directions of how you implement that idea, but the idea is There's a quantum state, it never collapses. And in addition, there are these local beables, particles, fields, whatever, that are guided by it, right? By the guidance equation. And then the behavior we see around us is the behavior of those things. And there's only one world made of those things. So it's not any worlds theory.
So would you say you're a proponent of Bohmian mechanics?
Yes, yes. That is the direction I think is correct, and the Bohmian mechanics part is the most highly researched and developed. Although, you know, the number of people working on it has been minuscule compared to.
Yeah, yeah. Well, what would you say then to Einstein, who, when confronted with the Bohmian paper 52, said the solution was too cheap?
Yeah, what I would say to Einstein, I think I wouldn't even have to say it. I like to think if Einstein had lived a few more years and seen Bell's result, and then seen the outcomes of the experiments, he would have been convinced. What he didn't like from the beginning about quantum mechanics was the non-locality. It's very clear. It wasn't the indeterminism, it was the non-locality. Yeah. And he played with things like Bohmian mechanics. I mean, you know, de Broglie had it almost instantaneously, or 1926, yeah. A kind of pilot wave picture. And Einstein played with pictures like that, and he always rejected them. I take it because they were manifestly non-local. Now, yeah. I think if Einstein had seen Bell's proof and then seen the experimental outcomes and said, well, you can't get away with a local theory, you know, he would have been upset, or he would have been surprised, or he would have been shocked. But I think he would have accepted it. And if he wasn't repelled by the non-locality, I think he would have been fine with it.
Okay. So you would agree then that non-locality is an absolutely essential part of the universe, the foundational elements of the universe, and that it's unquestionable?
Yes, I think that's what Bell proved, that the only way, and the nice thing is Bell's proof doesn't rely on quantum mechanics or anything, right? I mean, it's this very universal proof that says, you know, if you do experiments far away from each other and you have control over some parameters in the two rooms, here are some statistics that you cannot get with a local theory. And you get them. Yeah. So you can't do it with a local theory, okay? I think that's rock solid.
Okay, but if you then take non-locality as an essential element of the universe, you've got a problem. And the problem is on the other side of the great pillars of physics, two great pillars of physics, quantum mechanics and relativity. And relativity does not admit the idea of non-locality, or at least not in its form as it was originally presented. How do you square these two irreconcilable pictures? Of course, it's a picture, it's a problem which has been around for a long, long time. Quantum mechanics doesn't talk properly to relativity, and relativity doesn't talk to quantum mechanics, probably because of this central issue of non-locality. Is that how you see it? And what's the solution to that? And how
look, I agree that there's a tension there, and I think it's, I mean, irreconcilable is of course a very strong word because people can be very clever. I'm not that interested in reconciling it. So let me try and turn history on its head for a minute and try and convince you of something.
All right.
When Einstein wrote down special relativity, what he was trying to do was give an account essentially of Maxwellian electrodynamics, which is a local theory, which could perfectly well be happy in Minkowski spacetime. And then he took 10 years to give you a theory that was at least empirically very close to Newtonian gravitational theory, which is a local theory and would not predict violations of Bell's inequality, okay? So both special and general relativity were not built to explain violations of Bell's inequality because they had no reason to do that, right? Einstein was perfectly rational. And what they did was they got rid of absolute simultaneity, right? They got rid of a preferred foliation of the space-time. Well, he didn't need it. And if you don't need it and you can get rid of it and you have a nice clean theory, more power to you. Once you get violations of Bell and you say, okay, well, but how do I explain this? How do I implement this? The easy way to do it, and the way people sometimes say is too cheap, but I don't understand that rhetoric, is to put a foliation back in. Okay. Now that doesn't mean going back to Newton. I mean, if you want to keep a whole Lorentz signature relativistic manifold and add a foliation to it, fine.
So, sorry, what do you actually mean by adding a foliation to it to get those two reconciled? Can you give me some?
Well, you're not, I mean, if someone
example?
wants to say I'm rejecting relativity, I'm fine. I don't care the words you say. I mean, you have a manifold, you have a Lorentz metric, you have a Lorentz signature metric on it. Okay, that's some geometrical structure. I can just add a foliation to that structure. It's now a Lorentz signature metric with a preferred slicing, right? Time, space-like slicing, right? Space-like foliation. I have more structure than I had to begin with.
Okay.
Why did I add this structure? Because I needed to write down some equations. Like I needed to write down the guidance equation. Okay. And once I have it, it's kind of child's play to write down a guidance equation and to get violations of Bell's inequality. So that's the way I think you should go. I mean, personally, I think actually I'm working on a theory where there's a completely discrete space-time structure and the whole relativistic part sort of emerges from that, right? So but the underlying thing does have a preferred foliation. I think that's the right way to go. And I don't quite understand. I think the attachment to relativity doesn't make rational sense because, as I say, relativity was designed for local theories, and it's just not well suited to account for the actual non-locality we now know exists and that Einstein didn't know existed.
That moves us on towards the concluding part of our talk, and which takes us naturally into what you're doing at the moment, which you've mentioned is a discrete space-time. It's something I find personally interesting because my own PhD was on that kind of a subject area. Using algebras, but how are you envisaging your discrete space-time and what does it look like?
So as far as I know, it's a novel idea. It's something I call full discrete space-time because some people who've done discrete things, like you may know causal sets, they have kind of directed graphs. They replace a continuum with a directed graph, which kind of has only points and arrows in it, right? Kind of zero-dimensional and one-dimensional objects, if you will. Right. So my idea is to have a discrete space-time with zero-dimensional parts of it. You can think of them as points, one-dimensional parts, which are atomic lines that have the points as endpoints, two-dimensional, right, atomic areas, three-dimensional atomic volumes up to whatever the dimension of the space is. Now, we seem to only need 3 dimensions. So you have all of those elements. You can put fields on each of those elements, and you can sort of replicate your familiar continuum operators, curls and divergences and so on, with discrete operators on it. That all works out, as far as I can tell, very well. Then you have to put time in, which gets a little tricky.
So presumably you can generate things like Maxwell's equations. And
it looks like you can get things that look very much like Maxwell's equations, but discretized in a certain way. So, but yeah, the hope is to have a kind of pretty algorithmic translation scheme that'll take you from some continuum equations to these discrete equations. Of course, if you have a discrete underlying structure, you don't have to worry about singularities, right? You don't have to worry about the equations blowing up or going infinite. So you get rid of lots of problems that infect quantum field theory, right? And all the singularities that come when you do those things. So I think there are just lots of reasons to like going in this direction, but it's,
I agree. I mean, what kind of mathematical formalism are you using to embody your discrete elements? I mean, when I was looking at this kind of thing, I was using algebras to do that.
Yeah, I don't like algebra. I don't like numbers. Okay, I have this idea that the Greeks.
Now you're a philosopher.
Well, no, the Greeks divided mathematics into geometry and algebra and number theory, arithmetic. And they saw those as different. And the thing about it is, in the back of my head or in the front of my head at all times, when I'm doing mathematical physics, I'm asking, but why is this mathematics a good thing to represent the physical world? Okay.
No. Yeah.
And geometry, you think, okay, why would Euclidean geometry be good? And you might say, well, maybe space just has that structure. I mean, maybe space is a Euclidean, three-dimensional Euclidean space, right?
Locally, yeah.
But if you say, but what about numbers? Well, I don't know how to make the world out of numbers. There's no natural multiplication operation on physical objects. There's all kinds of, so I'm basically using just geometry and addition and subtraction. That's pretty much what I'm limiting myself to. And
Yes,
I'm trying to stay away from fancy algebraic notions.
But I mean, when you say some of these algebraic ideas incorporate important elements. So the algebra I was working on is something called the Weil algebra from Hermann Weil. And the if you just take two elements like A and B and multiply them together, then that's equal to omega, which is nth root of unity, multiplied by BA. So when it's kind of non-commutative kind of an algebra, but the non-commutation builds into it the kind of quantum theory ideas automatically. And it's not so much numbers, it's kind of just manipulating symbols. I thought it was it's the kind of thing I was doing myself, and I only did it because I found it very beautiful to work with as a structure. But from a simple relationship like that, out drops a Fourier relationship, and you get a Fourier relationship which then can relate beables like position and momentum, which you can then relate in that kind of a way. It's all built into very, very simple relationships. I just wondered if that's clearly the way you're going, though. With
it's not the way I'm going. Let me just say a word. I mean, I understand why that could be effective exactly for the reason you gave, that you have a kind of non-commutivity built in the way that, you know, Alain Kahn wants to talk about non-commutative geometries, which is kind of a fancy notion. And a lot of people see the non-commutivity as so central to quantum mechanics that if you're starting with a non-commutative object, you feel like you're going to get a lot of stuff very easily.
Yeah,
I think of the non-commutivity, I mean, there's one sense of non-commutivity as a physical kind of thing, but there you're talking about, well, what if I do this experiment followed by that one, as opposed to first this one, then that one? I mean, if you imagine, I have an experiment I call measuring position. I have another experiment I call measuring momentum. I can't do them both at the same time for physical reasons, right? I can't realize both experimental conditions simultaneously. And then there's a question, well, you know, would the results be different if I first do this one, then that one, or first do this one, then that one? That kind of non-commutivity, that's just physics, right? That's how does the time evolution go? And how does doing this experiment physically affect the system, which it should, right? It's not a surprise that doing an experiment physically affects the system. The non-commutivity that's built in to say what Kahn is doing, and I think what Weil is doing, although I don't really know it very well, is at a more fundamental mathematical level, right? Not in terms of time ordering, but it's just a multiplication, right? There's an abstract multiplication. And I don't know how to think about that physically. My problem is I don't know how to think about it physically.
Let me just suggest something. I mean, quaternions are probably the primitive form of this kind of non-commutative algebra. They beautifully represent rotation. So if you rotate one direction and then another way, that's the opposite of rotating it the other way and then this way. So you have the non-commutative effect of rotations built into quaternions. And I was told, I don't know where I read this now, but I was told that when Maxwell first produced his equations, he first did them in quaternions, which is quite startling because he wanted this kind of effect built into them. And it was someone like Gibbs who decided to get rid of all the quaternion stuff and put it into vector notation. But by building it out of that kind of structure, you build in the three-dimensional structures that you want automatically.
Yeah, I mean, again, I mean, as you can tell, I have a rant about everything. I'll rant.
I'm very interested in the
rant at you a second about this. So you think, okay, so the Greeks had geometry and arithmetic, and sort of you think of geometry. Okay, got Euclid, nice 13 books of Euclid, lots of stuff proven. You know, the great arithmetician was Nicomachus of Rhodes, who probably nobody, you know, very few people even heard of, and nobody studies. And for 2,000 years, between the two, a lot more interesting results in geometry than in number theory. But in the Middle Ages, you had algebraic method, this method of solving for unknowns using in number theory, right? And then Descartes, certainly among others, comes along and says, gosh, I wish I could use algebraic method to solve geometrical problems, and invents a way to do it. He's very self-aware of what he's doing. If you read La Géométrie, in order to do it, for example, he has to arbitrarily choose a geometrical unit because no geometrical length is naturally 1, but you need a 1 to correspond to the number 1, which is special. And the number 1 is special because you've got multiplication, because it's the multiplicative identity.
Yeah.
So you figure out a way to somehow introduce numbers in what to me strikes me as a rather artificial way, simply to have the power of algebraic method to solve the problems. But to me, the numbers get between the mathematics and the physical world, because as I say, I can see how the physical world could have in itself a geometrical structure. I don't really quite understand what it even means to say it has a numerical structure. Right? If you tell me the world is made of quaternions, I don't even know what you mean.
Yeah, fair enough. Fair enough. I think, yeah, it comes down, I suppose, to what the beables, what the foundational elements of the universe are.
Yes.
And some people would like to think of it that mathematics is the foundational universe, or the elements of mathematics. Maybe I think certainly Bohm was moving in the realm of looking at those kind of structures towards his last days.
I mean, Max Tegmark tried to argue that the physical world is literally a mathematical object, and all the mathematical objects are physical worlds. I mean, this kind of plurality of physical worlds, that doesn't strike me as being right. What seems to be true is that mathematics clearly provides really good means to represent the physical world. And there's a good question of why. I mean, for that to work, the math has to meet the world. Right, the world is not itself a mathematical, right? I mean, it's not a set of numbers or whatever. And then it's really interesting to think about, why does this math work so well?
Yeah,
representing what is the physical thing like, such that the mathematics provides me such an effective representation of it. And I think that's a really interesting question. And it invites you to take theories and reformulate them in different mathematical terms, to see if maybe if I reformulate it in these terms, the relation to the physical world will be more transparent.
Yeah, that was one of the questions on my list today. Why does mathematics represent reality so well? But we never got around to asking that particular one. Can I ask you one final question, Tim? And that is, where do you see the future of physics going? Are you maybe idealist enough to think or to hold the view that there's going to be a grand unified theory one day which will unite everything, and that's what we're really aiming for? Or do you think that's just a chimera, something which we'll never be able to achieve?
Well, I'm an optimist in that if by what you mean by a grand unified theory, what was originally meant, namely a single coherent theory from which both gravitational and all the effects we ascribe to the standard model, right, fall out of this one thing.
Yeah.
Yeah, I don't think that's beyond us. I don't see any reason to think that that's beyond us. It may be, again, that we'll actually end up with different proposals and not have an empirical way to decide between them. I would be more likely to think that we'll have multiple possibilities that we can't decide between than that will come up with zero possibilities. But, there's always this idea, maybe it's like, trying to teach calculus to a German shepherd, and we're just not smart enough to get there. I mean, there has to be a correct theory because the world actually exists, right? I mean, physics does manage to do quantum theory and relativity or gravity at the same time. So there has to be some coherent way to do it. And we've turned out to be awfully clever and clever in working out things going on at scales far beyond the mid-sized scale of the savannah where our brains evolved, right? We can go pretty far down into atomic realms and pretty far up into cosmological realms and still get things to work. So sure, I don't see why it would be beyond us to get at least that much put together.
Tim Maudlin, thank you ever so much for a very fascinating conversation. And if you'd like to follow up any of the ideas that we've been talking about, Tim Maudlin's got a couple of books which I can recommend. There's this one here, which is called Quantum Non-Locality and Relativity, particularly focusing on Bell's approach to quantum mechanics, and also this one here, The Philosophy of Physics, Quantum Theory by Tim Maudlin and produced by Princeton. Tim, thank you. Thanks very much indeed.